I thought a lot about what the audience might be like today, and I noticed in the minutes that were sent out about the attendees in advance that what I was seeing was there was a lot of new companies here today getting involved in QD, people that maybe I'd met before once or twice, but this is actually really encouraging for us as an industry to see new people coming and continuing to show interest in joining us in this industry. So I wanted to spend a little bit of time sharing our experiences in the past about what it took to make these devices successful commercially and how that looked from my perspective. And hopefully that's interesting for you and you gain a little bit of insight into what it might take for you as well going forward. And further give you a little bit of look at what we think the future is going to hold. So first off, about Nanosys. Excellent, we have a monitor too. So we're located in Silicon Valley. We're the first company to focus on quantum dots for electronic applications. We have achieved over $100 million in revenue in the last 5 years. We have been cash flow positive in the last 3 years. And all of this is based on the work that we've been doing with our quantum dot materials. We have the largest QD patent portfolio at over 320 granted and pre-grant applications, and we have about 100 employees. We operate a 60,000 square foot manufacturing facility, and that facility produces enough materials for about 6 million televisions a year. We also have a second facility which has just come online and is actually qualified now to ship product. And that facility has an additional 12 million units of television capacity a year. So we have capacity, we have customers and partnerships. We also have established, I think, ourselves as a leader in the display industry. So going back to 2011, we've had our first demonstration of a product using quantum dots in a display application together with LG. We won a Best of CES for enabling technology. In 2011 also, we won a Best in Show at SID. In 2012, Gold Component of the Year Award, and then 2013, 14, and 15 also Best in Show awards at SID. In 2014, in collaboration with Dolby for a professional reference monitor that was actually used to do the post-processing and creation, editing on the newest Star Wars movie. So for those of you who saw that, that was actually edited using quantum dots, so it's kind of a cool little factoid. Dolby actually won an Oscar for that PRM series of monitors this year as well, for those of you who watched the Academy Awards. So pretty cool to see our technology getting out there into the space in this way. Our business model is to manufacture and sell the world's leading performance quantum dot materials. We're not a component manufacturer, just purely material sales. We do, however, in the process of developing new materials, often develop component implementations. And so we license those to our partners, who in turn will make those components using our materials. And then we continue to develop new and innovative ways of using materials in the display space for future growth of our company. So, for example, our sample customer engagement, we're making the materials. We in turn provide those to one of our partners, such as 3M, who makes the optical components, such as the quantum dot film, who in turn provides it to display or set manufacturers, such as AUO, who integrates it into the television, and that in turn gets shipped under a brand such as Vizio. So this is actually the supply chain picture for the Vizio R series, which is in the market today. QDEF, our first component implementation in the market, is designed to be a drop-in replacement solution for the existing film stack that's used in LCDs. So in the existing LCD white backlight infrastructure, you have a back diffuser. The back diffuser, you remove that, and in its place, swap in a sheet of QDEF, switch from white LEDs to blue LEDs, which, as we heard Jenny talk about yesterday, are more efficient and lower cost, and then you have your QDEF implementation. And with that implementation, you get the high color gamut, you get the improved efficiency and all the other benefits that many people talked about yesterday. This has led to more than 20 products in the market. Many of these you can buy on Amazon today, ranging from the 7-inch Kindle Fire HDX all the way up to largest size is an 85-inch set today. Most of our connection to televisions is with UHD. And so as we see UHD coming on the scene, we're seeing a very high connect rate between quantum dots and UHD. Not a lot of action for us anyway, what we see between quantum dot technology and HD or older generations of display technology, but very good connection rate with UHD. Which leads us to our hypothesis, together with some data that we've taken from Jenny and others, that the ramp rate for quantum dot-based components is really going to follow a trend of UHD adoption. And so as UHD adoption grows, we think that the adoption of quantum dot technology will grow as well. This is measured in terms of square meters of display area, not in dollars. And so it's a way for us to think about how this will play out. Today, most of that orange that you see down there using quantum dots, those are high-end televisions. Those are large form factors, 55, 65 inches above the average. And those are feature-rich sets, as we talked about yesterday, wide dynamic range, high color gamut. And as UHD moves down in the price point space, it's incumbent on all of us to find solutions that can also scale down in terms of the economics that the consumer is willing to pay. So let's talk about commercialization, and I think any talk about commercialization has got to start with, foundation or innovation. And I just love this talk from Lou Bruce. He says, in 1982, when we first made this discovery, I didn't know what it meant in the beginning. One of the truisms in science is that the basic research scientists who invent something are not the best judges of where it's useful. It's really self-deprecating because in 1982, how could he have known it was going to be used in flat panel displays when there weren't any even flat panel displays, right? So it's a technology that evolved together with an entire industry, from fat panel to flat panel, from CCFL to LED to QD LED, and hopefully in the future to QLED. So this is a kind of foundational work. Our first commercial implementation of this was actually a military program, and it's not something that I saw mentioned yesterday in the roadmap review, so I thought I'd talk about it. We had a customer in the U.S. military back in the day. Nanosys worked a lot with military contracts, and there was a desire for the military to retrofit the heads-up display in the F-15 fighter plane with what they called a digital HUD. So this airframe was actually designed in the 1970s and uses analog display technology, analog CRT. And the image from the CRT is projected up onto some optics, and then that is, the pilot is able to see those images on the display screen. So this is the so-called heads-up display in the cockpit. The wavelength that they needed in order to make the conversion from a CRT projection system to an LCD with a backlight projection system was very specific, because they didn't want to have to retool all the optics in the plane. That would have been very expensive. So they wanted to just have a modular approach where they could swap out the existing CRT system with an LCD projector system and have the exact same color of image. It turned out it was green, projected up onto the screen. Now, there's no green LEDs at that time or even today with the necessary efficiency that they needed to get enough lumens up on the screen, so that this thing had to be daylight visible with the pilots, turning and going into the sun and all the rest of this type of stuff. So very high brightness, very demanding conditions. And keep in mind, this is 2006. So, what possible solution could we come up with to be able to use these, at that time, what we thought were very fragile nanocrystal structures in such a demanding environment? And our answer was high performance packaging. And so we created this really novel, I think, very clever design using sapphire plates for windows, sandwiching the QD material in between them. This whole thing was put together with a titanium heat sink, and this was all mounted onto a very serious metal core board that had 9 1-watt Cree LEDs that were just pumping out about 25 watts per square centimeter in order to get 850 lumens of green light up onto the backlight of the display. This system we were able to test at 850 lumens of green output for 4,000 hours at 50 C, and we basically saw no degradation. So when I joined the company, I was about halfway through this project, and it really made me realize that the nanocrystals are actually pretty robust. However, integration of the nanocrystals was really a big challenge, because obviously the military could afford to pay for one little tiny illuminator this sort of $5,000 that it was going to take to make these things have this high performance, but nobody else was going to be able to do that. So how could we take those materials and make them suitable for this type of application or even a commercial application without really getting into these kinds of price points? And that led to our second attempt at a commercial product. So in 2008, I launched a project together with LG to design an edge optic, what we call the quantum rail. This product was for mobile phones. At the time, again, OLED was something that people thought maybe was going to happen in mobile phones, but it hadn't happened yet. Clearly today, OLED has taken the majority share of smartphone displays and seems like it's going to continue to grow strong in that area. But in 2008, this was still an open field and lots of units. So we worked on how to encapsulate the material in a way that would allow it to have the lifetime necessary to crank out 500 nits in a display, have very low color drift, very low color tolerance, or the tolerance for color differential across the display was very, very tight at less than 0.005 U prime V prime, and had to operate for 30,000 hours. So again, we turned to our old friend, high performance packaging. And so in this case, we opted for a glass capillary type solution. We made this solution, you can see a drawing of the implementation here, the blue LED with the quantum dots on a flex, all lined up next to the LGP, very, very tight. This entire assembly, you probably can't see in the back, but the Y dimension, I guess I have a laser here. The Y dimension on this is 200 microns, and this is about 600 microns. And so the precision that was necessary to make this component and integrate it was very difficult. Nevertheless, we came up with lots of really unique things like laser end sealing, where we were able to seal these ends of these capillaries within about 100 microns of the end, with no gap in the QD material, which was, again, very critical because there's just not a lot of real estate inside of a phone. We were able to make a lot of great devices together with LG, but ultimately this form factor was just really tough. And just one of the many things that we had issues with, I've shown in this picture, which is when you just have a very, very, very thin layer of this material and you're trying to cross-link it inside of this sealed tube, voids form and bubbles form and defects form. And not every single time, and there's a lot you can try and do about it, but at the end of the day, you can imagine that this affects your optical performance, so the optical transfer function through the device if you've got one of these types of defects in front of your LED versus you don't have one in front of your LED. And this is an industry that is cranking out 300 million units a year, so 1% defect rate means you're making 3 million bad phones. It's just totally not acceptable, right? So, and we could never get close to 1% defect rate. So this project, unfortunately, also did not succeed. I forgot to mention the F-15 didn't go forward because the Pentagon decided that they wanted to spend more money than what that program was going to cost. So they bought the F-35, which costs $1 trillion a plane now. So, you know, they could have bought quantum dot illuminators for $5,000, but they bought the F-35 instead. So there you go. So, you know, this solution just really turned out to not have the kind of yield performance at the scale that was necessary for the mobile industry. So we took that learning and, you know, we turned to another implementation, and that's the film implementation. And so we started to design and work on the film in 2010. We developed this program ourselves. We actually set up a pilot coating line. In 2012, we met up with 3M and formed a partnership, and they became our customer for materials. Together with them, we were able to produce 100% NTSC and greater than 100% NTSC, such as 90% Rec 2020 films that did maintain that very low color, very high color uniformity across the field, even across a large field. Had very good part-to-part variation, and that could stand up to this sort of 1,000 nit backlight brightness over 30,000 hours. But we really couldn't turn again to high-performance packaging, so we had to do something different. And so our solution here really was improving the material durability. So while we tried packaging as a solution to implement quantum dots a bunch of times, and I just showed 2 examples up there, ultimately it was about making the material suitable or compatible for a low-cost packaging solution that made the product become commercially successful. And this is what you have to keep in mind. So we went from a hermetic package to a very, about 10 to the minus 6 level of laser sealed capillary to a ultra barrier film. In terms of the moisture and oxygen ingress, this was a 3 or 4 order of magnitude improvement in terms of the sensitivity of the material to degradation over, again, 5 to 10 years of use life, 30,000 hours of operating life. So in order to hit the price points, some of the things in addition, we could not have an edge seal on the film. Edge sealing, very expensive, not very reliable, so had to be able to cut this stuff and ship it. The barrier requirements couldn't be too high. We had to be able to get near perfect coating uniformity across runs, coating runs, 1,000 meters in length, sometimes longer than that. And a system that could be cost effectively scaled to millions of units annually. And we've had some great partners, and 3M certainly been one of them to help make that happen. But nevertheless, it wouldn't have been possible without improvements in the materials. Still, this required a barrier film that was in the $10 to $20 per square meter range, and 2 sheets of that per square meter because you make a sandwich. So, you've got $20 to $40 of barrier film in a product that really wants to be sold for about $40 or maybe even less. So that's still a problem, and a lot of people talked about that last year, how that was an issue with pricing. So, we kept working on it, and this year we have materials now which are in production today, which are using so-called food-grade optical, but food-grade optical barrier films. And we have materials coming very shortly to the market, which are actually air processable. So a lot of our customers, what we found, they need to be able to mix these things, load lock them in and out of their coating machines, et cetera, using non-inerted environments. They just don't have that level of sophistication in their factories. It's really interesting. We go into some of the coating factories, we say, oh, we just need a nitrogen blanket over this. They're like, we don't have nitrogen. We're like, what do you mean you don't have nitrogen? Oh, we don't have it. It doesn't come to the building. So they literally have no nitrogen in the whole building, right? So it's just a completely different set of people who are really able to make these kind of low-cost products, and their infrastructure is just completely different. So we have to make more durable materials. If we can't make durable materials, then we're not going to be able to get these costs down. And the Generation 5 materials that we have, which I've shown a picture of here, which we've tested, actually on plain PET, well, optical grade, we're getting more than 170,000 hours of life out of these. These are some oxide-coated indium phosphide, zinc sulfide quantum dots. And so they're basically getting a local layer of encapsulation around the dots instead of a package level layer of encapsulation to prevent the moisture and oxygen ingress. These materials being sampled to our customers today for MP next year. I also just want to talk a little bit about the regulatory issues. Now, of course, we heard yesterday how there's a regulatory uncertainty leading to confusion in the marketplace, and I don't disagree with that. But I think it's also important to note that the two major CE companies on Earth will not put cadmium into their products, and so Samsung nor Apple. And so the rest of the industry, we have to look carefully and think to ourselves, okay, regardless of what the regulation says, these guys really do control a tremendous amount of both market share and mind share. I think it's incumbent on us as an industry to look at how to develop better non-cadmium based materials. And so we've been doing that for several years now, and actually our revenue mix has been steadily shifting away from our cad selenide based materials, and this year we'll get close to 50% of our revenues coming from non-cadmium based materials. We think that there is still a performance gap. There is no question about that. In fact, we showed that at SID last year. But we need to continue to work on narrowing that performance gap, and for those applications where the customers are willing to accept the existing performance, or for new implementations, new types of configurations besides backlight phosphor applications, these materials may have very good performance characteristics even today. We also received in the last year, we're the first company in the world to receive a PMN clearance for quantum dot manufacturing. So we actually can legally in the US manufacture over 20 tons of our material on an annual basis. Obviously that's a big milestone to make sure that we've got the capacity that's necessary for meeting the demands of this industry. One last comment. As was said yesterday, there's a lot of different ways to skin the cat as far as implementation and how you put quantum dots into your display. I think there's merits in all of these. All of them, however, depend upon higher durability materials. And going forward, we've got to continue to improve the durability. Whether that means they go into an LED package, or they go into an edge optic, or they go into a film, it's going to be necessary for all of those things. So if you want to work on something, that's really the place where, I would say the industry needs help. We're getting there, but obviously everybody working together on this problem will help get us all there faster. And getting there faster is important because there's a big thing coming. And we can argue all day about what the best implementation into LEDs for quantum dots is, but the day is going to come when there are no LEDs in displays. Do not make any mistake about it. I don't know if it's going to be in 3 years or 5 years or 10 years, but that day is coming. And when emissive display technology comes, we need to be ready for an Act 2, or we need to be ready to evolve the use of our materials to be useful in emissive displays. And again, in order to do that, future emissive display architectures, we believe strongly, continue to require improved material durability. You're going to have to be able to put these things in resists. You're going to have to be able to etch them. You're going to have to be able to process them through high temperature bakes and lots of other semiconductor types of processes. And ultimately, we hope that this will lead to novel and breakthrough emissive devices such as QLEDs. So in summary, we've led the commercialization of the technology. It's been a real fun thing to do. Gotten over $100 million in revenues over the last 5 years from this technology. We have very good visibility into end customer usage and adoption rates, and think that quantum dots will be as important to UHD as LEDs were to HD for as long as there are LCDs. But there may not be LCDs forever, so we better start thinking about the day after that. And ever increasing the durability and environmental acceptance of these materials is going to be also critical for us going forward into the future, both to compete against new phosphors as they come. We've seen a few of those in the last few years, but also against new emissive architectures such as OLED. So with that, I'd like to wrap up and say thank you. See if there's any questions.
Thanks, Jason, for that very nice overview. It's really impressive how you guys have improved the environmental robustness of your orders of magnitude. So for an LED die, I have to ask the question, how many more orders of magnitude of stability are required for on-chip performance? Because if I look at your momentum, it just begs the question that maybe it's not so far away. While I understand your comment about displays and LEDs go away, for lighting is not the case. And there's a real revolution, I think, potentially possible if we go from sheets or films or rods in lighting to on-chip performance.
Yeah, so I do believe that that will be possible. As far as the precise date when that's going to happen and the selection of the material, I think those two things are somewhat linked. So the best performance in those types of applications today, as you know, and we've talked, is based around CAD selenide dots. Those are the furthest and most mature. I think we've got some of the furthest and most mature non-CAD selenide based dots for that type of application that there are. But I would not say that we have more than 1,000 hours of lifetime performance in that kind of environment yet. So, does that mean that you're going to wait for non-CAD selenide dots, and you might be waiting a few more years, or 3 more years, or 4 more years? I've heard talk that there should be products with CAD selenide based dots in the market within a year. Not ours, so it's just a rumor as far as I know. But I think that this will happen, and I think the time frame around which that will happen will depend on choice of material system and performance characteristics.
Jason, thanks for the talk, and it's definitely impressive to see the growth that you've seen over the last few years. I'm curious, though, with respect to the thought process around licensing in Korea versus material sales, and sort of the Visio application that you showed up there in terms of, you have a licensing deal with the OEM that's going to bring the most products to market. Was that mostly the decision to go that path versus the traditional, the 3M and Visio that you showed up there, around the CAD versus non-CAD? Or did that have more to do with the idea that that market would be locally sourced and really wouldn't have the chance to sell the materials into that market?
That's a good question, Jed. So at the time when Samsung wanted to launch that product, we did not have capacity to provide suitable performing cad-free materials to them. And they absolutely were not going to use cadmium-based materials. So we've been working on it, and we've been working on developing that technology with them since 2009, actually. There's a JDA that is publicly stated in a press release that we had with them. But we were not ready with a manufacturing capacity for that. And I think that it caught us by surprise, to be honest with you, because the reason we weren't ready was the performance gap that we just talked about. It's real. And so, from our perspective, why would people adopt this technology when there's such a huge performance gap? And so we had gone down the path of, well, performance is everything. And we had a lot of great partners who had told us, based on their experience, people pay for energy efficiency. People pay for, making sure that they get every last photon out of the device. And so if you've got a more efficient material, that's what we should be ramping up. And so that's what we did. We ramped up our CAD selenide capability in that time frame. And then, post Samsung's major launch, became apparent that there's a market for non-cadmium based materials that's substantial. And so, we were left with, obviously, we developed a technology and we could have a nice, lucrative licensing deal on it, not for NREs, but real licensing dollars. Or, we could go without anything. And the choice is pretty obvious at that point.
And so when your non-CAD materials are at that performance and you can supply, does the agreement allow you to come back into that market as a second source supplier?
Yeah, so I can't tell you what's in the agreement, but we can sell materials to Samsung, and we do sell materials to Samsung.
Any other questions for Jason? We'll let him off the hook then.
All right, thank you.